Good afternoon, everyone. My name is José Conradi Hoffmann, and I'm going to present for you today the Timed Data, a real-time pitch in ECRTS 2021 by Professor Antônio Augusto Fröhlich and me. Periods and deadlines are the key concepts sustaining the design of most real-time systems, and a quite common depiction of these systems is the one presented in this slide. This strategy has proved effective and has been enforced since the 60s. However, the AI revolution we are living in is mostly driven by data. So, where is the data? How does such models address concerns, for instance, network, memory, and even security? We believe that if AI is to find its place within data-driven critical systems, then we must learn to design and implement such systems around the data they handle instead of the tasks they run. A data-centric or data-driven embedded system design models data in a broader sense. The figure presented here depicts a control loop of such system, with sensors generating inputs for AI models, fusion, mode of operation rules that guide a controller for actuation in the autonomous vehicle. From physical data sources like sensors and data storage to the data that drive the actuators or must persist, an intensive data flow must be handled in such systems by coordinating sensor networks, networks on chip, security, base access, and so on. In this scenario, tasks become elements of the transformational data that ephemerally exists to perform fusion, aggregations, and all sorts of transformation. Data is what remains, data is what must be secured, exchanged, stored, and processed. So why not arrange data with temporal attributes and model critical systems around them? This wild and crazy idea talk introduces SmartData, a concept that supports a data-centric design of critical systems. SmartData enriches traditional data with timing, location, security, and semantic metadata while modeling input, transformational, and output elements of a data-centric design. These smart data classes are a direct map from the real-world scenario with smart data instances for sensor, transformers, and actuators. The timeliness of data can be expressed through an expiry, which represents the last moment in time they can be used without compromising any of the system requirements. The expiry is then propagated from the actuators to the transformers and sensor smart data through the dependency relation, where the expiry is an attribute of the relation itself, and the smart data supplying the actuation adapt their sampling accordingly. Moreover, smart data can be extended to build time series of multiple smart data by passively monitoring the data interactions and storing the results in historical buffers for further AI retraining and so on. This is called a multi-smart data. Stored data can also be modeled as a sensor smart data, where access to the data returns previously stored samples of a specific sensor, transducer, or actuator. Through smart data, we can globally assess systems characteristics. Data has size, physical resources as capacity estimates to handle data, networks have bandwidth estimates, stream processing units have throughput estimates, sensors and actuators have response time estimates. In many cases, worst cases are known, and for many others, there are stochastic models. All in all, system-wide latency can be more promptly derived from data that must never expire than from tasks that must never miss their deadlines while manipulating data. Finally, freshness of data can also be promoted by replacing this traditional early job release perspective with a just-in-time update. As a comic association, we can see data view of smart data through the cooking. Adding the right ingredients to a stew while managing each one of the ingredients' specificities will increase the chances of producing a tasty meal. As enriching the data modeling with the right metadata like timing, size, security needs, location, dependency will enable building data-driven system designs through the data itself. Thus, as our final remarks, enriching this data with meaningful metadata like timing requirements while modeling input, transformational, and output elements of the data-driven design enables assessing the global characteristics of the systems beyond traditional scheduling, adding confidentiality, availability, integrity, and latency notions, while mapping specific data to AI accelerators. These are the main references of Lisha works over the last year addressing smart data, which based this work. That was it. Thank you.